Welcome to Lesson 3, Example 8, and what it is asking for is, excuse me, it tells you have a glued laminated 5 1/8 inch beam wide times, well, they don't let you know what, but they say 1.5 inch laminations, and it spans 30 foot. Then we got 30 foot. I drew that real quick, and it says dead load including its own weight is 300 PLF. And then it also says it has a roof live load of 600 PLF. It says use combination, let's write that down, 24F V1, which has actually it goes ahead and tells us allowable bending stress, which is good. We don't have to use the table. Equals 2400 PSI. And allowable horizontal shear stress, FV, equals 140 psi. Remember, these are allowable, so this is the maximum that we can have, maximum stress. It says what size beam should be used. Do not consider deflection or the volume of the beam. So remember, when we're designing something, we need to look at, let's write a straighter line there. Typically what you'll do is you'll design for a moment, or let's do bending. Say bending. It's the same thing in essence. Bending, or what you can also call it flexure. And then number 2 is you are checking. You want to check shear, and then you want to check deflection. Sometimes they call it deformation, or not. We'll call it deflection because that's what I'm used to calling it. Alright, but it's saying that we don't have to do this. And then it's also giving us, this is for, it's giving us the maximum stress in bending. It's giving us the maximum stress in shear. So let's go back to our thought process of how do we start this. Well, we could do shear and moment diagrams, which are pretty darn easy, and this is a very simple one. And we'd first have to solve for our reactions, and then we'd have to draw our shear and our moment diagrams, which at this point, hopefully you also notice that it's got two distributed loads, and that we have equations already thrown out for this. And this is what you're going to see 90% of the time for your equivalent live load here. Not equivalent live load, but equally distributed live load. I'm running low on brain cells tonight, but it's WO squared over 8, and we want to do that for dead load, and then we'll do it for live load as well. And if we need to combine them ahead, we'll go ahead and do that as well. Welcome to Lesson 3, Example 8, and it is asking us to figure out how tall this beam is. What type of beam do we want to design for given that it's 5 1/8 inches thick, or wide, let's say, and you're using 1.5 inch laminations, and then this 30-foot span. You have this is a 600 PLF roof live load, and that's important. And wood members that support roof are given a 1.25 increase in capacity. Let's just start capacity. And then 300 PLF for dead load. And it also says to use 24F V1, which it gives us the allowable bending stress and the allowable shear stress. It also says do not check deflection. Deflection is not an issue. So remember, in our design procedure, we kind of always want to design for bending first, and then we want to check shear, and then we want to check deflection, but we don't have to do deflection in this example. So let's go ahead and proceed. What you could do is you could do shear and moment diagrams to figure out what your max shear is, and then moment. But of course, we see this and we say, oh well, that's equivalently distributed load, and When we have those, we know it's going to be a WL squared over 8 for max moment equals WL squared over 8. And we also know that max shear equals WL over 2. And you can look that up in your steel book, or there's other analysis books that have it. You could also go ahead and do shear and moment diagrams to prove that to yourself. But since we have this 125% capacity, if you have live load, we have to go ahead and separate these out and then do it. You have to figure out what is your max allowable going to be for dead load only, and then what is your max going to be if it's with live load at 125%. So let's go ahead and get this out. And you can just tell by looking at it, it's twice as much live load, so it doesn't, this 125% capacity is not going to, do it. If you had 125% of this, what's 300 times 1.25, then it might work, or somewhere around there. But when you have that much live load compared to your dead load, live load plus dead load is going to control. But let's go ahead and do both. Alright, so let's say M live load only, WL squared over, I'll tell you what, we don't need to do WL squared over 8. It's going to be 600 PLF times L, which is 300, or 30, sorry, squared over 8. And that's 600 times 30 squared divided by 8. Get 67,500 foot-pounds. Now let's go dead load only. 300 PLF. 30 foot divided by 8. And it should be half of this. But let's go ahead and do it just in case. 33,750. And that's half of it. That's in foot-pounds. Alright. And then let's go ahead and do Vmax as well for both. V live load equals, actually let's just go ahead and do M total load equals 67,500 times 1.5 or plus 33,750 equals 101,250 foot-pounds. And then let's go over here and do shear. Actually, let's go ahead and do bending. Let's just proceed, and then we'll check for shear as I've lined out in our design. Alright, so let's remember what we need to get the stress. Right now we have moment, and you might be thinking, okay, well, where do I go from here? Remember, the stress in bending equals M over S or MC over I. But we're going to go ahead and do M over S. And what we're going to be solving for, since we're looking for what size we need, we're looking for S. And since we have a max FB, we're going to go ahead and substitute this for that and use it as FB max. So we have 2400 PSI equals something over S. Alright. And let's do dead load only. Let's do M dead load. So this is dead load only, meaning we're not going to increase our capacity at all. Foot-pounds. Remember, S is going to be in, this is S minimum, because anything higher than that's alright. And this is going to be in inches cubed, so we want to get this to inches. So let's go ahead and put foot on the bottom, 12 inches on top, and then let's go ahead and calculate or solve for S. S min, let's call it DL, S min DL only, and that will equal 33,750 times 12 divided by 2400. That's 168. 0.75 inches cubed. Alright. Now let's go ahead and do M total load, meaning we need to increase it by 1.25. So in essence, you're going to be 1.25 times 2400. We'll just put it on this side so it's a little bit more intuitive. You could put it over here in your equation, but it's easier to follow this way. So remember, we're hitting this by this 1.25 factor. We're increasing the capacity. We're increasing the allowable because it's a live load, and that's a certain type of live load, the roof live load. And because of that, it tells you since you're hitting it with this roof live load, that's not going to happen all the time, which means it's probably snow plus maybe wind. You know, worst case scenario, it's in a blizzard, and during a blizzard, you're also not going to get all these other loads. You know, the dead load's not going to be that bad, and you can overstress it a little bit, and it'll be all right. So let's continue. Then you want equals M live. M total loads. Excuse me. Go ahead and erase that. M live load plus dead load, which is total load, over S. And we want to put that up there. 101, 250 foot-pounds. We want to change it to inches. Then S min TL, we'll call it. Solve for it. Excuse me. S min TL. And that equals 405 inches cubed. Now let's ask which one's going to control. So let's say something in the middle. And you say, okay, well, if I have 200 inches, it says S min. No, it'll work. It'll work for there. And it says the minimum. No, it won't work for that. So what's going to control is your higher minimum. I hope that makes sense. I'm not going to explain it because I think it's intuitive there. So this is what is going to control. So now we need to go into your table and figure out what size of 5.1/8 beam it works for. So we go to a table on page 56, and it go down to your width, 5.1/8, and just go down until we get over 405 for S. So we go down 405. I would say 5.1/8 times 22.5, and you get 432.4 for S. And that was how tall? 22.5 inches. Let's check that. And they got the same on the example study guide. 5.1/8 times 22. And now we need to check shear. And we're running low on time, so I gotta pick up pace a little bit here. Check shear, and FV equals the short equation is over BD, which BD equals A. And we can go ahead and put this equation in here, which, let's go ahead and write it up here. Vmax equals, add them 300 plus 600 is 900 times L, which is 30 foot, over 2 equals 13,500 pounds. Let's put this in here. 3 times 13,500. And remember, we're going to have to increase the allowable, which was 140, and our A is 115.3, and that comes from that graph, that chart as well. And that's inches squared, and this equals 175.6 psi. Remember, we have to increase the allowable though. And allowable up here we said was 140, so we have to say FV equals 140 times 1.25, and that equals 175. So it's right at it, and we'll just say, you know, okay, it's good, close enough. And what we'd say in engineering is, you know, this is what 0.0% 1% overstressed, and that's good. So this would be the design.